Okay, atmospheric science students, here's the second of the three little videos that I'm going to be making for you with regard to demonstrating Newton's method on an Excel spreadsheet. Here I'm going to have you find a root or zero of the function g of x equals pi sine of pi x to the pi power. Okay, I deliberately made a weird equation here with lots of pi's in it because I just want to show you a particular feature. Here's what an equation looks like, by the way, when it's plotted. It's a really interesting little example of what's called a chirp function. A chirp function gets faster and faster as it oscillates faster and faster the farther out the x-axis you get. And we can see that somewhere near 1.4 there is some kind of place where the equation crosses the x-axis. There's a root of the equation. Now, we're going to need g of x and we're going to need g prime of x because that's how Newton's method works. And g prime of x, I've worked it out beforehand, is pi cubed times x to the pi minus 1 power times the cosine of pi x to the pi power. The reason why I chose the equation so weird is listen to all those pi's that are in there. Now, if you sit there and try to type in 3.14159 every time you heard the word pi in that equation, you're going to just have a big old mess going on here. It's better if you could define the word pi to be 3.14159. Well, that's called a name in Excel, and names are awfully handy. Here I happen to have defined a name. I put the value of pi right here. Now, actually, in the case of pi, there actually is a function. You can actually see, whoops, sorry. I kind of cheated here. If you look at the formula bar, equals pi, open parentheses, close parentheses, actually already means pi in Excel. But if we didn't know that, I just went ahead, could have typed 3.14159.3 whatever in this cell, and then I could name that cell. That's actually what this little bar over here to the left of the formula bar is for. Let me do you another example real quick. Let's just say I wanted to say grade, and that's just a label here. I'm just putting this here for my sake, and I'm going to say 98. That's my grade. I know it's a little bit underneath that, but that doesn't hurt anything. I select that cell, which is currently D2. If I just go in here and call that grade, now grade is a name for that cell. So, like, for example, if I want to say equals 100 plus grade over here in this cell, I get 198. Okay, grade just becomes kind of like a constant in Excel, and that can be a really handy trick. Plus, if I change the value of grade over here, let's say I change it to 88, notice any place that depended on it has changed as well. Well, okay, so I defined a constant here called pi. But I mean, I could have whatever. It could have been whatever I wanted it to. But you can well imagine that when you're working with like an Excel spreadsheet where you're trying to make some equations based on physical meteorology or something, where you might have a whole bunch of constants, giving them a bunch of names, and then you can just write your equation out as C1 times I times ms times the mass divided by the mass equals whatever, and you just can be working with it a little bit less with the D's and the D1 and D5 and XX3 and all that are the symbols that the addresses you use in Excel. Okay, again, I'm going to switch this to a slightly more zoomed in view so you can see how we're going to do this one here. And again, I'm just demonstrating another example of Newton's method. In this case, I'm going to use a name for pi since there's so many pi's in this equation. All right, so again, our first guess, and I said that we're going to guess starting at 1.4 because we know that's fairly near the right answer here. G of xn. If we go back here and look, g of xn is pi sine of pi x to the pi power. Okay, so that is equal to, now here's my defined name, pi times the sine of pi times, okay, x. X is this value 1 to the left, right? Raised to the pi power. Raised to is the caret symbol above the 6 on your keyboard. Pi power. Pi times sine of the quantity pi times f32 raised to the pi power. Looks good to me. And that's the number that we get right there. Okay, now g prime. I worked it on paper beforehand. It is pi to the third power times the quantity x. Again, x is 2 over there to the left. It's f32. Raised to the pi minus 1 power, and let's see, times the cosine of pi times x to the pi power. All right, did I make that work right? Yep, okay, great. All right, so that's g prime, which makes x of n plus 1, the second guess, is equal to x of n minus g divided by g prime. And that gives us our second guess for our value of xn. All right, remember a nifty trick for getting the second row to work is plus 1 plus, or let me be more clear, equals this one plus 1. That gives us a 2. Our x2 is just this equation right there. And these equations we get to just reuse by copying and pasting them over here. Notice how these are all relative references except for the constant pi. Okay, well, it's not so much that it's a constant, it's that it's a name. Okay, and you can see that we come up with a new guess, x3, which is 4.1. I mean, it's barely different than our first guess. In fact, if I copy this row and just paste it down a couple more rows, you can see that our value of x of n just has pretty much settled down at 1.4186. And in fact, when you plug that value into g of x n, you get a number times 10 to the negative 15th power. That's about as close to 0 as you're going to get. So we have solved this using Newton's method. In this particular case, we took advantage of the fact that we could use a defined name to make the writing of the equation a little bit simpler. Let me show you one more example on the next video.